Hey nerds! The heavy hitters of sci-fi fandom all start with Star. First we had Trek, then came Wars, and then came Gate. Starting as a movie back in 1994, we had the dream team of Kurt Russell and James Spader. But then it moved into a whole new level of fandom with the TV series SG-1, headed by MacGyver himself. And then it ran for 10 seasons, spawning movies, games, and a wider universe. We had Stargate Atlantis, the OG Jason Momoa show. That was the first time. Momoa, Atlantis. Oh my god, I'm only realizing it now. Anyway, then we had Stargate Universe, of course, which we are all still freaking waiting for season 3. Where is it? Trek had warp drive, Wars had hyperspace, and Gate had wormholes. But there is another piece of iconic technology that this show brought to pop culture, rooted in real quantum theory, but subject to grifters and snake oil salesmen, and so deeply misunderstood that conspiracy theories abound. And that's zero-point energy. Stargate Atlantis introduces us to zero-point modules, ZPMs, technology of the ancients that powers the city. These devices extract vacuum energy from an artificially created region of subspace time, and they continue to function until that region reaches maximum entropy. Now, the term subspace, as in Star Trek, is fictional terminology that the show uses to kind of hand-wave around some real physics limitations, but the inclusion of it and the idea of maximum entropy shows that the writers were at least thinking about the very real physics. A ZPM is more like a very advanced battery, but this makes it good science fiction because it takes a real physics concept in zero-point energy and then adds fictional technology to create this internally consistent power source. Now, you guys know that I love me some plausible deniability when it comes to the physics in my fiction. I don't need it to be perfect. But like I said, we are dealing with a real topic here, zero-point energy, and that is the lowest possible energy state of a quantum system. The term comes directly from quantum mechanics, and it appears throughout legitimate physics literature starting way back in 1911 with Max Planck. The quantum vacuum, then, the lowest energy state of quantum fields, genuinely has properties that lead to observable effects, things like the Casimir force, the Lamb shift, and modifications to atomic behavior. This is all established, uncontroversial physics. The problem begins when people hear zero-point energy is real and then take a hop, step, and a leap to, oh, then we could build generators to extract it as a free energy source. Now, this usually comes from two different sources, right? The first are, maybe somewhat well-meaning confusion from people who have heard about vacuum fluctuations and they just don't understand why they can't be tapped. But the second, well, they're deliberate grifts from people who are selling free energy devices or soliciting investment for technologies that essentially violate thermodynamics. The grift version as well often invokes Nikola Tesla. The comments will be riddled with it. They talk about government suppression, disappeared inventors, patents are evidence of, these devices are out there. None of this constitutes scientific proof. And I want to be clear as well about Tesla here, because Tesla was a genuine electrical engineering genius who did real groundbreaking work. But people misunderstand his work in wireless technology as related to zero-point energy. He never worked on it, but zero-point energy does exist. The thing is, there is no known way to extract it as usable net energy. And every free energy version either violates thermodynamics, misunderstands quantum field theory, or adds energy from somewhere else. So in this episode, we are going to look at what zero-point energy actually means in physics, why certain real effects like the Casimir force don't provide free energy, and why every zero-point energy generator is just another version of a perpetual motion machine, but with fancier terminology. I'm Abby, and this is Pop Culture Science, Zero-Point Energy Explained. I just want to ask that if you like what I do, then please do interact with this video and subscribe to the channel so that I can keep bringing you these deep dives into the science of fiction. Anyway, let's start with the basics. What does 0 point actually mean? 0 point energy refers to the lowest possible energy state of a quantum system. It's like the energy that it still has even when it's cooled all the way down to nearly absolute zero. Now, in classical physics, you could in principle cool a system until all motion stops. But quantum mechanics forbids this through the Heisenberg uncertainty principle. This is one of the fundamental concepts that we have in quantum mechanics, and it says that there is a limit to the precision with which certain pairs of physical properties can be simultaneously known. Basically, you cannot know with absolute certainty both of the quantities at the same time. And the most important relationships here are energy and time, and then position and momentum. A quantum state has a lifetime, and that lifetime is related to how much energy it has. So like really energetic particles like the Higgs boson, they have like very, very short lifetimes. And if you want to measure its momentum with some certainty, then you can't know exactly where it is. The energy-time uncertainty leads to the conclusion that no quantum system can ever have zero energy, because zero energy leads to implications that it also has zero uncertainty in position and momentum, which violates everything that we know about quantum mechanics. So even in the ground state, there must be some leftover motion, some like irreducible energy. And this is the 0 point energy. The term appears in two related but different concepts that I think a lot of people tend to confuse. Now, first off, there's the 0 point energy of bound systems. So we're talking about like atoms and molecules, mechanical oscillators. So if we look at a simple harmonic oscillator in quantum mechanics, it has a ground state energy of 1/2 h bar omega. Now, h bar is the reduced Planck constant, and then omega is the angular frequency. This value, like this is the energy here that remains even when the oscillator is in its lowest quantum state. So for molecular vibrations, this means that molecules continue vibrating even near absolute zero temperature. And we know that this is true because we can measure it. But the second way that is talked about is the 0 point energy of quantum fields. Now, in quantum field theory, even empty space, the vacuum, it's not truly empty. Fields exist everywhere. So you've got the photon fields, the electron field, the Higgs field, and so on. Like all the fundamental particles in quantum field theory have an associated field. These are what gives rise to the fundamental particles in the standard model of particle physics, and those fields have quantum fluctuations, even when they're in their lowest energy state. Now, each mode of the field, and when I say mode, what I mean is the allowable energy states or frequencies that the fields can occupy. So each one of these modes contributes a ground state energy. When you add up all possible modes, you get what's called the vacuum energy. We can think of 0 point energy as the unavoidable residual ground state energy in both material systems and fields. And we do have ways to measure the effects of it, and we can talk about some of those examples. Starting with liquid helium-4, because this never freezes into a solid. Now, normally when you cool a liquid, the atoms will slow down and attractive forces pull them together into a crystal lattice. And then you get like ice or frozen nitrogen or whatever it is you're cooling. But helium-4 stays liquid all the way down to the lowest temperature we can get to, at normal atmospheric pressure, to be clear. It just refuses to freeze. The reason is that helium atoms are very light, and momentum depends on mass, which means their quantum uncertainty in position is relatively large. Even in the ground state, they're jiggling with 0 point motion, and that 0 point kinetic energy is large enough that it overcomes those attractive forces that are trying to lock the atoms into a crystal. The atoms are just moving too much quantum mechanically to ever settle down into a solid. Now, you can force helium-4 to freeze, but you'd have to apply about 25 atmospheres of pressure to push the atoms close enough together that the attractive forces finally win. If you did this experiment, you are looking at a direct macroscopic consequence of zero-point motion. You can literally see it by cooling helium-4 and watching it not freeze. Another example we can look at is something called the Lamb shift. According to the Dirac equation in quantum theory, two particular energy levels in hydrogen should be exactly the same, but they're not. There's like a tiny difference. And this shift comes from the electron interacting with vacuum fluctuations of the electromagnetic field. Now, it was measured by Willis Lamb in 1947, and the discovery won him a Nobel Prize because it proved vacuum fluctuations have real measurable effects on atoms. And similar to this, another example is if you put an atom inside a specially designed cavity, the rate at which it spontaneously emits light changes compared to an atom in free space. Now, the cavity changes which electromagnetic field modes are available, which affects how the atom interacts with the vacuum. This is called cavity quantum electrodynamics, and it's used in really practical applications like building better atomic clocks and quantum computers. And yes, of course, we have the Casimir effect, but we're going to talk about that a little bit later. The main point that I want to get across here is that zero-point energy and vacuum fluctuations are real concepts, and they have observable, measurable consequences. The effects are genuine physics, they're not just mathematical artifacts. However, and this is the most crucial part of it, having observable consequences doesn't mean that you can then extract net energy. The vacuum is already in its lowest accessible energy state. Just because that state has structure and leads to measurable effects doesn't mean that it can be used as a fuel source. To understand this, we're going to first need to explain what the quantum vacuum actually is. In quantum field theory, the vacuum is defined as the lowest energy state of all of the quantum fields. It's not empty in the classical sense because fields themselves are fundamental. They exist everywhere in space-time. Even when there is no particle present, the fields are still there and they still have quantum properties. The problem we tend to see in the media is how vacuum fluctuations get popularized. The most common description that you'll see is this idea of virtual particle-antiparticle pairs popping in and out of existence. The idea being that they borrow energy from the vacuum very briefly, but then they annihilate before becoming real within the universe, and so there's no violation of thermodynamics. And you've probably heard it explained like this before. It shows up in popular science books, it's in documentaries, some textbooks. I've definitely spoken about it before. But the picture can be framed in a very misleading way. Virtual particles appear in Feynman diagrams, which are visual representations of mathematical terms in quantum field theory calculations. Those diagrams are incredibly useful and they give correct predictions, but the virtual particles in them are not literal objects popping in and out of existence. They're just mathematical intermediate states in a calculation. They don't have well-defined energy or momentum, and they don't travel through space, and they're not borrowing any energy. So when physicists talk about vacuum fluctuations being real, we're not actually talking about particles. Now, since fields can't be perfectly still, they have quantum properties, even in their ground state, and so they still interact with real particles and they affect measurements. What we call fluctuations refers to the quantum uncertainty in field values. So phenomena like the Lamb shift and the Casimir force are real physical effects that arise from how quantum fields behave when they're in their ground state. What we call the vacuum, despite being empty, can interact with matter because it has quantum properties, because it's filled with quantum fields. So what we call vacuum energy is real, and vacuum effects are real, but tapping into them as a power source, that's kind of where the physics and the fiction part ways, which brings us back to Stargate. So the 0 Point module is one of the most iconic pieces of technology in the Stargate franchise, even though it wasn't introduced until pretty late with Stargate Atlantis. ZPMs are technology created by the ancients, one of the most advanced civilizations in the universe, and they're presented as these crystal-like power sources of enormous capacity. Now, according to plot, ZPMs extract vacuum energy from an artificially created pocket of subspace time until that pocket reaches maximum entropy. And this, you guys, is clever science fiction. And it's clever for a number of reasons here, right? Because firstly, it doesn't claim infinite energy. The ZPM depletes over time like a battery, so throughout the series, when they find ZPMs, they have to ration power. They're always out there searching for new ones, and there's a big major issue when one of them breaks. The show explicitly acknowledges that even this incredibly advanced technology has limits. Secondly, the show also invents the necessary fictional components. Real physics doesn't give us artificial subspace time pockets, you guys. It doesn't give us a way to create a controllable non-equilibrium vacuum state, and it doesn't give us any containment structures that can safely extract energy from vacuum fluctuations. Stargate acknowledges all of this by making ZPM's technology that is beyond current human capability, something that requires some fictional advancement in science in order to achieve. Now, they also include things like failure modes and risks. If you have a damaged or a malfunctioning ZPM, that is a dangerous piece of equipment. They can explode and fail catastrophically, so they need careful handling. They're not presented as just push a button and get infinite power. They need engineering and maintenance. But the most important thing that they bring up in this story is that the entropy limit is crucial. By saying that this artificial pocket reaches maximum entropy, the show is acknowledging thermodynamics. So entropy is a measure of disorder, or it's the number of possible microscopic states of a system. When a system reaches maximum entropy, it's reaching equilibrium. And when that happens, there is no more useful energy to be extracted. This is exactly the thermodynamic constraint that real physics imposes. You can't extract work from a system that's already at equilibrium. So what Stargate does is takes real physics concepts and then adds in this fictional technology to create something that feels completely plausible within its own universe. The ZPM doesn't violate thermodynamics, it just posits a fictional reservoir that can be depleted according to the rules of thermodynamics. Compare that to how free energy grifters present their 0 Point energy devices. Because they skip all of the engineering limitations and they claim that they can extract unlimited energy from the vacuum using ordinary materials and known physics. They remove any limitation. They keep only the promise of this infinite free power. That's the main difference between science fiction and a scam. Science fiction is at least a consistent story. The ZPM is never presented as something humans could build or reverse engineer easily. Even after studying ZPMs for years, humans in the Stargate universe can't manufacture new ones. They're relics of this far more advanced civilization. It's aspirational technology, not something that you could supposedly build in your garage with instructions from a YouTube video. So why does the ZPM need those limits? Why can't you just extract energy from the vacuum indefinitely? Because useful energy requires something fundamental. There has to be a difference that you can exploit. The main confusion that seems to appear with these zero-point energy grifts is this leap from the vacuum has energy to, oh, well, then we can use that energy. And understanding why this doesn't work requires understanding what makes energy useful in the first place. So energy can be a hard concept to understand because it's simply defined as the capacity to do work. Work is a process. It's when you apply a force over a distance and this action transfers energy. And the amount of work done on an object is the same as the change in its kinetic energy. So work is whatever process you use to transfer energy. So to get energy, you need to, in physics terms, do work. In order to move energy, you need a gradient, some imbalance that lets you transition from a higher energy state to a lower energy state. You don't get work from a system that is in a uniform state. You get work from energy flowing or transforming between different states. This is fundamental thermodynamics. Let me give you some examples. Heat engines. Heat flows from hot to cold, and you can then extract work from that flow. Hydroelectric power. Water flows from high elevation to low elevation, and you can extract work from that flow. Combustion. Chemical reactions proceed from reactants to products, releasing energy in the process. Electrical power. Electric charge flows from high potential to low potential through a circuit. And pneumatic engines, where compressed gas expands from high pressure to low pressure. In every case, there is a difference, a gradient that drives the process and allows work extraction. The second law of thermodynamics formalizes this, that systems evolve towards equilibrium, towards a maximum entropy, where there is no more useful work that can be extracted. Once a system reaches equilibrium, you can't get any more work out of it. This is why the vacuum has zero-point energy doesn't mean we can use it as an energy source, because there's no process that you can do that will move that energy from the vacuum to another place, because there's no state for the vacuum to move into, like no lower state. Let's use water as an analogy, right? You have a glass of water, and when molecules move around, they have a temperature. If you reduce their temperature, they don't move around as much, so they get colder. So if you remove energy from the water, you can, in theory, use it. But the process of taking the energy from the system, like from your glass of water, makes the water colder, eventually freezing it. Once you have ice, there's no more energy for you to remove. The ice isn't going to transition again so that you can take out energy. But the ice itself still has energy because the molecules still move around, they just move a lot slower. Now, I just want to take a moment for the well actually crowd here, because yes, we could get into Bose-Einstein condensate, but that is overcomplicating a simple analogy, so let's not go there. Think of the ice as the vacuum. It has energy, but there's no process you can do in your kitchen that will take that energy from the ice, because you would need the ice to change into something with lower energy. Stargate's ZPM avoids the problem using fiction, positing its artificial pocket of spacetime that starts in a non-equilibrium state, a state with available energy that can flow towards maximum entropy while powering devices. Real physics doesn't give us any sort of a reservoir that we can talk about. There's nothing even speculative realistically. The vacuum we actually inhabit is, as far as we know, already in its ground state. But Abby, what about? I know what you're gonna say. Like, I know what, like, come on, yes, there are some well-known cases in experiment and theory where it can appear that energy is coming from the vacuum. But these are all misleading, or they're at least misrepresented online. In each case, energy is being converted, not created from nothing. So let's talk about a few of these: the Casimir effect, Schwinger pairs, and Hawking radiation. I've spoken about the Casimir effect a number of times before because it always comes up when we talk about warp drive. So if you are a regular here, then you should be very familiar with the general idea. Two conducting plates attract each other in a vacuum. As they come together, you can extract work. The process is related to the modes that are allowed between the plates versus what's allowed outside the plates, which leads to pressure pushing them closer together. And this is a sort of a quirk where the energy density then appears to be lower between the plates than the vacuum energy, which leads to claims about like negative energy. And this is why it gets talked about a lot when it comes up in warp drive discussions. But what I want to make clear here is that the energy comes from the system, not the vacuum. What's unique is that these vacuum fluctuations allow for the energy to be moved around. So the vacuum is acting like a medium that moves the energy around, the energy that becomes accessible from the experimental system. It is not being pulled from the vacuum itself. Another important point is that it's a one-way system, right? If you want to repeat this process, you have to reset the plates again, which means you have to pull them apart, which costs energy. And it actually costs you more energy to separate the plates than you get from them coming together. Now, at some point, I think I will do a dedicated video on this, explaining the experiment in more detail. And there was also another one in 2011 called the dynamic Casimir effect that uses superconducting circuits. So don't worry for now about how it all works. The important information is that energy is being moved around, not created. Now, the second and third cases that I mentioned are related to each other, and that's Schwinger pairs and Hawking radiation. Real particles can be created using the vacuum in extreme conditions, so near black holes or in strong electric fields. Let's start with Hawking radiation. Now, the popular explanation involves particle pairs, like electron-positron pairs, and the idea is that they're being created near the event horizon of a black hole. And most people will then say that these are particles popping into existence due to vacuum fluctuations, which kind of sounds like saying that they're just appearing out of nowhere and it's just energy being created. The more accurate version is that these particles are produced when a black hole radiates away its own mass energy. Now, in physics terms, different observers will disagree about what counts as particles near a black hole, and the net result is that energy escapes and the black hole shrinks. The black hole is the power source, not the vacuum. For stellar mass black holes, Hawking radiation would be incredibly weak. Like, the value makes it colder than the cosmic microwave background, which means that they would emit less radiation energy than they actually gain just from the background of space, which is why we have never detected Hawking radiation. Only tiny micro black holes would emit enough energy for us to detect, but we've also never observed any micro black holes. Another effect that involves creating electron-positron pairs using the vacuum is the Schwinger effect. This is related to strong electric fields, so something like a very, very, very high power laser. Above a critical field strength, which is about 1.3 by 10 to the 18 volts per meter, the claim is that the fields can pull virtual pairs and make them real. Now, a quick caveat here is that this field strength is about 1,000 times stronger than anything that we can sustain in any lab, so we have never done it. But as another aside though, I was recently involved in an experiment that was published in Nature where we were able to create incredibly high intensity X-rays using a process called coherent harmonic focusing. Now, I'll pop the video link in the description if you want to know more about that, because it brings us closer to being able to reach the Schwinger limit, which is really cool and really exciting. Anyway, what's more important about this idea is that the energy that creates these particle pairs comes from the electric field itself, not the vacuum. The process would convert some of the field's stored energy, so some of the energy from the laser into particle mass energy. The vacuum acts as a medium, allowing the process to happen, but the energy is still being transferred from one system to another. It's not being created from nothing or being pulled out of the nothingness of the vacuum. In both cases, particles emerge from the vacuum, but the energy comes from an identifiable source, the black hole's mass or the electric field's stored energy. The vacuum participates in the process. It acts as a medium because it has the properties that allows for the transformation because it's filled with quantum fields, but it's not supplying the fuel. So, why do people think otherwise? Why is there this persistent belief that the vacuum contains these enormous amounts of extractable energy? Well, it comes back to a calculation from quantum field theory that is the energy bros go-to proof. But is it true? Whenever I challenge zero-point energy champions online, they will always respond with some form of, but Richard Feynman and John Wheeler calculated that the vacuum energy in a single light bulb is enough to boil off all of the oceans. It appears in countless articles. It's in YouTube videos, consistent across Reddit threads and pop science books, as apparent evidence that the vacuum contains this unimaginably vast extractable energy. The problem is tracing where this claim actually comes from. Now, the clearest mainstream reference that I can find appears in a 2003 Guardian article that states that Wheeler and Feynman calculated that the vacuum energy inside a single light bulb could boil the world's oceans. However, the Guardian article doesn't cite a specific paper or publication where this calculation appears. It's presented as an established fact without any source. And it seems to be almost impossible to trace the claim to its origin. It comes up in Wikipedia entries, in, like articles online, pop science books, many a YouTube and TikTok video, but there's no clear primary source that tells us where or when this actually happened, whether it was published, whether it was a specific calculation. It seems to be a summary or maybe a paraphrase of something that they might have said or wrote. It could have been in an interview, maybe even a lecture, but the actual source is completely unclear. So we can't take that as scientific proof or evidence for these claims. But does it mean that it's not real, or like that the idea isn't real? Well, we can't actually figure out what it's probably talking about. So what the quote might be referring to is summing up the zero-point energy across all the different ways the electromagnetic field can vibrate. You can think of it like a guitar string. So a guitar string can vibrate at its fundamental frequency or at what are called overtones, which are higher frequencies. An electromagnetic field is similar. It can vibrate in many different patterns and each at a different frequency. Now, each of these vibrational patterns has some ground state energy. And if you add up the ground state energy from every possible vibrational pattern up to some arbitrary high frequency cutoff, the total grows like insanely fast. The bigger the cutoff you choose, the bigger the number. And this is how you can get to enough energy to boil the oceans contained in a light bulb. That's why it's worth being clear what that figure does and doesn't include. The boil the oceans number comes from just one field, the electromagnetic field. But the electromagnetic field is only one of the quantum fields that fill space. There's a field for the electron, for each type of quark, for the Higgs, and so on. When we talk about the predicted value of the vacuum energy, we mean the contribution from all of those fields combined, not just light. And it's worth noting that some of those fields have a negative contribution. So the light bulb quote and then the full vacuum prediction are two different parts of the same idea, one field versus every field. Either way, the reason that the number comes out so insanely large isn't about how many fields you include. It's about how high you push that cutoff, since the energy grows with roughly like the fourth power of it. And since that cutoff frequency is arbitrary, there is no agreed upon reason to stop counting at one frequency instead of another, so you could, in theory, go all the way up to infinity. This is where quantum field theory brings in a tool to handle infinity, and it's something called renormalization. Now, we do not need to get into that. We're not going to get into that. What you need to know is that you can choose different cutoffs, which will make the vacuum energy number different by 60 orders of magnitude. The vacuum energy can basically be set to any value in quantum field theory using renormalization, depending on what regularization scheme you choose as the cutoff. Now, another big factor here is that in quantum field theory, what matters observationally is energy differences, not absolute values. It's not about the number of possible energy states. It's about the difference between two of them. You can shift all of your energy values up or down this scale and the physics stays the same. So this huge calculated number doesn't necessarily mean anything physical. It's just an artifact of how you're counting. But the biggest issue with this enormous number for vacuum energy is one of the most well-known problems in cosmology, the cosmological constant problem, or what's called vacuum catastrophe. Using the method in QFT that we just talked about, we can calculate that the vacuum could have an energy density of around 10 to the power of 113 joules per cubic meter on one end, or about 10 to the power of 56 on the other end. Remember, this depends on how you apply renormalization. But when cosmologists actually measure the energy density of the universe, because we can do that through observations of cosmic expansion, they find something that we call dark energy, with a measured density of only about 10 to the power of -9 joules per cubic meter. Dark energy appears to be an intrinsic property of the vacuum, and dark energy is uniformly distributed throughout the vacuum. This is important because in general relativity, energy curves spacetime. It affects how gravity works and how the universe expands. If the vacuum really had all of the energy that the theory predicts, like that really, really high number, whether it's 10 to the 56 or 10 to the 113, it would have curved spacetime so dramatically that the universe would have expanded impossibly fast after the Big Bang. Like galaxies, stars, and atoms could never have formed and we wouldn't exist. But we do, I don't know if you noticed. So either the theoretical prediction is wrong, something is suppressing the effect, or our understanding of how vacuum energy works is incomplete. This is one of the biggest unsolved mysteries in physics, but the mystery is about why the prediction doesn't match the actual measurement. It's not about hidden extractable energy. The light bulb quote, or the idea, it's not evidence that free energy is available. It's an indication that we don't fully understand vacuum energy. It highlights the gap between what quantum field theory predicts and what the universe actually does. And that gap is a genuine mystery. But guys, come on. The mystery isn't, why is the government hiding my 0-point generator? So let's say that we're going to be generous. We're going to assume that the observed vacuum energy density, like the dark energy density, the stuff that's actually out there, we're going to assume, let's say, somehow that could be tapped. How much power could you actually extract? Well, we can do some math. Now, like I said, the actual measured value of vacuum energy is 10 to the -9 joules per cubic meter. This is genuinely tiny. A modern day LED light bulb uses about 10 watts. That's 10 joules per second. So if you wanted to power that bulb using the observed vacuum energy / dark energy density, you'd need to extract it from about 10 to the 10 cubic meters of space every single second. That is a cube roughly 2 kilometers on each side, every second. continuously, just to power one singular light bulb. Oh, and sidebar, once you've taken it out from that one region, like, it's gone. I was thinking about this and I worked out, if you could do this in the space between the Earth and the Moon, you would get enough energy to power that light bulb for 53 hours. Like, that's it. That within the space between the planet and the Moon, you get 53 hours worth of a 10-watt light bulb powering. I kind of feel like we're doing better with the energy processes that we currently have. Now, just as a little sidebar, in case anyone is confused, dark matter and dark energy are not the same thing, and they are not related. We just call them both dark because they are dark to us. We can't see it, so we can't determine what exactly it's made of, but they are different concepts and entirely different things. So, we've talked about the real physics. We know that vacuum energy exists and that certain effects are real, but extracting net energy from a ground state needs a lower energy destination. That means that every zero-point energy machine ever proposed can only get around this problem in one way. They have to violate thermodynamics. A working zero-point energy generator would need to be able to extract energy from the lowest energy state, but as we've already said, a system in its ground state has nowhere lower to go energetically. Now, you might be thinking, well, what if we're wrong about the lowest energy state? What if there is a lower energy it can go to? And that's a fair question, but it opens up an entirely different and much more dramatic problem. You see, according to what we know so far, it is possible that our vacuum could be metastable. That means that we could be in some sort of a local minimum. So we're stable for now, but there could theoretically exist a lower energy, the true vacuum that our universe could transition to, like a ball sitting in a valley when there's like a deeper valley somewhere else. And the Higgs boson mass measurements from 2012 do suggest that our vacuum could be metastable. This leads zero-point energy grifters to be excited because, like, it's a solution, you guys. If we're actually in a metastable state, then there is a possibility that we can go lower. But to do so would trigger vacuum decay, one of the most spectacular ways that the universe could end. If this is true, our vacuum could theoretically undergo a phase transition. And if this happened, then a bubble of true vacuum would spontaneously nucleate somewhere, like a quantum fluctuation at extremely high energy density could cause it in the early universe, or in principle triggered by something. And that bubble would then expand outward at the speed of light. And inside that bubble, the laws of physics would be different. There would be different coupling constants, different masses for particles, different force strengths. The expanding bubble would be an expanding sphere of entirely different physics, consuming everything in its path. The universe inside the bubble would be uninhabitable to us. It would be the end of our universe in a single flash. But guys, don't start panicking though. That doesn't mean that there's going to be a sudden pop right now while you're watching this video. The possible time frame for the current stable state is about like 10 to the power of 100 years. So like, we're good for now. But what if someone actually could engineer a way to trigger this transition by creating a device to extract energy by forcing a change to this lower energy state? Well, that would be genuinely terrifying. Like, if you had technology capable of triggering a vacuum transition, you'd have much bigger problems than power generation. Like, real vacuum engineering, if possible, would be one of the most dangerous things imaginable for the entire universe. The only people supporting this must be suffering from a serious existential crisis if they want this to succeed. But, like, The truth is that we don't need to worry about this because no zero-point energy machine actually does what it claims. They're all just like bad electronics with pseudoscientific language. Every single one of them ignores the problems or claims to have solved them without demonstrating anything. So how do the grifters get around their lack of proof? Now, a quick sidebar before I get into this next section here, because these claims and discussions are almost always American-centric. Like things like flat Earth, moon landing, zero-point energy, they all tend to center around big government conspiracies almost exclusively in the United States. That's not to say that people in other countries don't hold these ideas. It's just not as big a thing in other parts of the world. And there's also a much bigger focus in the US on how they see their position and influence on the world. Now, we see it online all of the time. A lot of people from the US struggle to understand the world that exists outside their own bubble. Now, I do agree that the US government has been involved in secrecy and covert operations, including experimenting on its own people. There's absolutely no denying that. But science is a global language. Like, you cannot hide breakthroughs from the global community, and the US doesn't control the scientific output of the world. If there was a scientifically proven way to create a zero-point energy machine, someone somewhere else would figure it out. So let's talk about why this idea of government suppression and secrecy just doesn't hold up. The "they're hiding it" narrative relies on several beliefs: that patents are proof of function, that government investigation is proof of validity, and that global suppression is plausible. Now, a patent is a legal document granting exclusive rights to an invention. It requires the invention to be novel and described in enough detail that someone skilled in the field could theoretically build it. But, and this is incredibly important, you guys, what a patent does not require is proof that the device works or that it does what the inventor is claiming it does. You do not need to present a prototype or any physical proof that the invention actually works. You can just submit drawings, and if they look reasonable enough, you can get a patent. There are no physicists or engineers going through these documents and checking the math to make sure that they make sense. Now, the US Patent Office did historically refuse to examine things like perpetual motion machines based on the grounds that they were thermodynamically impossible by definition. But this changed back in the 1990s, partly because the office just decided that it should remain neutral on fundamental physics questions and apparently let the courts sort it out if necessary. And this change in policy has led to multiple patents for zero-point energy devices. However, what it has not resulted in, I don't know if you've noticed, is a flood of working perpetual motion machines. The existence of patents tells you that someone filed a legal claim about a design. It does not tell you that the design works. And if you really think about this, right, is if you had a working free energy device, that would be immediately profitable. Like, you could power a data center, you could power a manufacturing facility, an island, a spacecraft. You could license the technology to every single engineering company on Earth and become the wealthiest person in history. I'm pretty sure there's an Asimov short story similar to that relating to atomic power. Like, you wouldn't need to convince anyone of anything because the device itself would convince them by just, making their electricity bill zero. So why doesn't this happen? Well, they claim that it's because it's being suppressed. But this idea requires this implausibly large coordinated global conspiracy. The "they" would have to include fossil fuel companies who are competitors with each other, motivated to undercut each other. It would also have to include governments who, tend to go to war against each other. We also have militaries who would clearly weaponize free energy immediately, and then universities who are always competing for prestige and breakthroughs. You also have independent research labs, you have rival nations, you have countless individual scientists motivated by career advancement and Nobel Prize potential. For a global suppression to work, you have to have all of these people deciding to suppress it, communicating that decision across all of these institutional boundaries, and then enforcing it indefinitely. You then also have the idea that could someone really keep, or like, could one nation keep it a secret from another nation without weaponizing the free energy technology if they discovered it first? You'd also have to resist the financial incentive to commercialize it. They'd have to suppress independent researchers who might stumble onto the same idea, which is a hell of a lot more likely than you're thinking it is. And they'd have to suppress inventors, investors, and whistleblowers. The coordination needed makes this less plausible than the much simpler explanation that the device doesn't work. If something doesn't work, you don't need coordination to suppress it because it suppresses itself through the simple fact of like not producing the claimed results when it's tested independently. History provides examples of suppression of ideas, absolutely. But they typically involve ideas that threaten power structures. So like early heliocentrism threatened religious authority and evolution threatened certain interpretations of scripture. But I don't know if you've noticed, neither of those things remained suppressed. Suppression also tends to fail relatively quickly as evidence accumulates. What doesn't happen is a century-long, worldwide, perfectly coordinated suppression of a repeatable experiment. Now, once you're willing to believe that something is being suppressed, that perceived secrecy itself starts to become evidence to you that there's importance there. But the absence of public information about something is not evidence that the something is real or important or that it's being kept a secret. Ideas that don't work just fall by the wayside all of the time. If you claim that evidence for free energy was classified, you're just moving the burden of proof to a realm where you can't provide evidence. You're claiming that proof exists but is hidden, which is unfalsifiable. You're moving into the realm of faith and religion. And this is not how scientific claims work. But another aspect to this government suppression idea is the lone inventor, this small group with breakthrough knowledge facing opposition from the scientific establishment. Big science refuses to look outside its prejudices. This plays into like this compelling story that we tend to see on TV a lot of the time about like this, an underdog genius against the establishment. But the truth is that science just doesn't work that way at an institutional level. Breakthroughs in physics don't happen with one person alone in a lab. The days of that are like 100 years ago. They happen now across multiple labs. There are teams of people. The work gets published, others ask questions and then point out flaws, and then the work is repeated and refined, it's tested further, it's presented again and again and again to the whole community. The more important the breakthrough, the faster it spreads, because everyone then wants to use it and get involved in the research. This concept of mainstream science, it's just a way for grifters to push their pseudoscience claims. The argument that science is rigid and won't explore beyond its boundaries is so completely opposite of the action of actually using science. The point is that we have to push the boundaries. We have to try to break what we know and understand in order to find new things. That's what we do every day, and the weirder the better. If someone had genuinely discovered zero-point energy extraction, they wouldn't be unknown or marginalized. They would be the most discussed physicist alive. Multiple independent groups would be replicating the results right now. The discovery would be transformative enough that no amount of suppression could contain it. I was trying to think of a way that I could get this point across, and I was thinking about atomic physics, right? And splitting the atom. Because yes, the Manhattan Project was a fairly well-kept secret, as in the purpose of the project, like the fact that they were building the atomic bomb was a secret. But every physicist and chemist on the planet knew what fission implied, and everyone was working on it once it happened. They weren't all trying to build an atomic bomb, but they all knew it could be done. And since then, we have relied on nuclear energy and we are actively working towards nuclear fusion. They couldn't keep the science a secret. So why would zero-point energy be any different? But what's really interesting is the effort that people will go to try to continue to push this idea. There will be true believers who will be persistent in these claims. There will be people in the comments. We all know it, despite everything that I have said so far. But the main thing that we need to acknowledge is that there has been no mainstream adoption because nobody can replicate the work of anyone that is claiming anything. But what that leads to is them presenting these increasingly elaborate explanations for why mainstream science is closed-minded. They then form this bubble of online support that reinforces their story for them. But that's not proof of suppression. That's just a community of people who are invested in a belief that hasn't met the threshold of evidence needed to be taken seriously. The scientific standard is independent replication. That's it. If someone makes a discovery, others should be able to reproduce it. If a discovery is genuine, it doesn't disappear when one person dies or leaves the field. Claims that depend on vanished evidence, dead inventors, they're not scientific claims. They're just bad science fiction, because that is the truth of all of this. None of their stories are as good as the fiction that Stargate gave us. Now that we know more about what zero-point energy is and the challenges of trying to extract vacuum energy, we should understand why Stargate ZPMs are good, internally consistent fiction that plays with physics as we know it, using it in a clever way. Now, in order to extract zero-point energy from the vacuum, we need a lower energy state for it to transition into. This doesn't exist in our universe unless we find we are in a metastable state, in which case transitioning to the true vacuum would, destroy the entire universe. So, to make it work as a story, we need a fictional pocket of space or some sort of a field configuration that isn't in the ground state, like this artificial region of subspace-time that Stargate creates. Now, if we are breaking through to this pocket of subspace, then we need some form of a stable containment structure. We need a way to keep it intact and shield it. Like all great sci-fi, they invoke crystals. Dilithium, Kyber, all the stars have a good crystal structure to control their energy flow. Now, to be fair, crystals are pretty foundational to modern electronics, so it fits. Obviously, though, they are fictional crystals being used in a very fictional way, but it does make logical sense for the technology that they're presenting. The ZPM is not some free energy source that goes on forever. It's a fancy future battery that eventually runs out because it follows the laws of thermodynamics. As you use the stored energy, the pocket evolves towards equilibrium until it reaches maximum entropy and it's depleted. All of this creates a reasonable but very fictional piece of technology. It acts in line with how an energy source would act on a fairly basic level. Stored energy that depletes over time. No complaints here. Now compare all of this to what the grifters claim. They remove all the realistic limitations and they keep only the promise. They claim ordinary materials, not like this technology of the ancients, can extract unlimited energy and work indefinitely. They say that you will never need a replacement. They skip any logic or understanding of science that would make it even remotely internally consistent as fiction, never mind a real piece of technology. Stargate's ZPM works as science fiction because it respects thermodynamic limits even while inventing an impossible technology. The Grifters' ZPE machines only work as a story because people want to believe in it, not because it's in any way realistic. Stargate is sci-fi. ZPE machines are fantasy.
Okay, snap! That's it! You're happy now?
Rodney!
Now, you guys, I am glad that I finally got to do a Stargate topic, and it was a bonus for me to finally cover one of the grift topics because I have wanted to talk about it for a long time. Like, I once made a short video on here about ZP maybe 3 years ago now. I still get comments on it. It's a big one in the like hype bro realm, but look, if they put as much of their time, effort, and funding into fusion, we might have it by now. But people don't seem to want to do the hard work. They want the quick and easy solution, but then they're also willing to put all of their energy into achieving the easy way out. I don't understand it. They do this so much that they are willing to believe in magic. Now, yes, people will bring up the Arthur C. Clarke quote where he said that any sufficiently advanced technology would be indistinguishable to magic to us, for sure. But we do not live in a universe with the ancients. We live in the real world with real physical constraints on technology. No scientist is truly against advancements, new discoveries, or like breakthrough ideas. We want all of that. Every time this happens, a whole field full of opportunities opens up. But we are against pushing pseudoscience and false claims and using anti-establishment language as a way to not have to present your findings. If nobody can replicate it, it doesn't work. Thanks for watching. If you're new here, I'm Abby, I'm a physicist, and I love to talk about the science of science fiction and some of the big questions in physics. Now, if there are any topics that you want me to do a deep dive on, then please do let me know and I will get researching. And also, you guys, can I just ask, because YouTube has this like new feature where you can hype a video. I think you have to do it in the first week that it's out. I would really appreciate it if you would do that and help me to grow on here. Because like I research, write, record, edit all of my videos myself, while also trying to finish writing my thesis for my PhD. So please do subscribe if you haven't, and like if you haven't. And if you liked this video, well, you might like my video on why human teleportation can't work. Or you can check out my deep dive playlist here. Now, one other thing is for my Patreon and YouTube members, I haven't picked what the bonus video is going to be for this topic this month yet. So if you have requests, get them in. And yeah, stay nerdy.